Yes, sure.
Can we use Mathematica in solving problems?
Okay, yes and no. All right, so what do I mean by that? So the question is, can we use Mathematica for solving homeworks? Um, yes, in the sense that like it's really handy for arithmetic, particularly with the numerical integration. Okay, but you should be able to at least set everything up by hand. Okay, so Mathematica is a tool. It can do everything and make you a sandwich. Well, maybe not quite, but pretty close, right? So yeah, it's a tool. Feel free to use the tool, but use it wisely. Okay, because what don't you have when you take fluency assessments? Mathematica, right? It's just you and a piece of paper. So yeah, keep that in mind. Um, yeah. All right. Well, let's get to it. So last time we were kind of talking about how uh, you can find the volume, or sorry, the area between two curves if you kind of, and you can do it in lots of different ways. So I could slice things this way, I could slice things that way, and I could write multiple different integrals that might represent the area of some particular shape of my choosing. Okay, so what we're going to do today is kick all this stuff up into a third dimension. Sound fun? No? Well, I could have said let's kick it up to a fourth dimension. That'd be fun. A little harder to draw the pictures. Okay, so the idea here would be what would happen if I took, so let me just draw kind of a cheesy picture here, right? So what would happen if I took, um, why are we not getting, hold on. One moment, technical difficulties. I was having this problem yesterday with my pencil not wanting to pencil. Um, all right, let's try this again. There it goes. Okay. So yeah, they must have messed up the app because it seems to want make me restart it a whole bunch. So okay, so we should have the iPad back up on the screen here in a minute. There it goes. Okay, so let's just imagine. So I'm going to draw a straight line here, and then I'm going to draw like some sort of like curve there. All right, so that kind of looks like the letter B. Um, and then what I want you to imagine is that I take this thing and I spin it around the red straight line. Okay, what's it going to produce? It's going to make some sort of solid object, okay, that's going to kind of look like, well, my art skills really suck, but can you guys kind of imagine what it might look like? Okay, or here, let me actually, like spun around violin, yeah. Okay, all right, let me choose a like slightly easier example to draw for my own sanity. Let's say that I take a right triangle and I spin it around. What am I going to get? I'm going to get a cone, right? Something that looks like that. Huh? We can keep the violin shape. It's just harder for me to draw what it would look like after you spin it around that axis, right? Because I'm not an artist. Okay. You discovered that last period.
That egg hand whisk thing is going great.
Yeah, well, let me show you guys the pathetic picture I drew last time, or last my last class. We were talking about. So what do you think this means? Okay, and crack it. See, this is a. I was attempting to draw hand cracking an egg, and yeah, that's the best I could come up with, right? So um, yeah, they'll hire just anybody around here. Oops. All right. So let's take, the cone, right? Now, do you guys happen to know the volume formula for a cone off the top of your head? What is it? You forgot it? Okay. Jack? Okay, that's the volume of a sphere. Okay. Yeah. The height? Yeah, pi r squared times the height. That's the volume of a cylinder. The volume of a cone is one-third that. Okay. Um, well, we could prove why that's the case. Well, yes, using calculus, right? So what I want to do is so let me come down here and draw my right triangle again. Okay. And let me call this quantity h and this quantity r. Okay. And then I need to come up with an equation for um, this this line, right? So what is its y-intercept? Well, okay, so let me say that this is at h and this is at 0. Okay, so that the entire length is h units. Okay, and then let me say that, well, let me call this 0 and that the number capital R. And then I'm going to think of, well, actually, you know what? Why am I making it capital R? Because I'm going to make both of them capital, actually. And the reason is that I want to think of little h and little r as being variables, and capital H and capital R as being the specific height and radius of the full object. Okay, so what would be the equation involving little h and little r for the line that describes the hypotenuse? Well, where is its y-intercept? Well, so, sorry, it would be h, right? H would equal slope times radius plus intercept. Okay, so what's the slope of that thing? Well, it drops capital H units and runs capital R units. So the slope should be negative capital H over capital R. Right? Does that make sense? Okay, so if I put the origin here, right, at the where the right angle is in the triangle, I mean, I can put it anywhere I want, but um, uh, well, what do I need to do to write down the equation of a line? I need to know a point and I need to know the slope, okay? Or I need to know the y-intercept and the slope, either way. So in this case, it's real easy to see where the y-intercept is. It's up here at capital H units up, okay? So that's why I've got the plus capital H at the end there, because that's where the intercept is, okay? Then I need to know what would go in front of the x, if you will, would be whatever the slope is. Well, what's the slope of that line? It drops capital H units and runs capital R units. So the slope is rise over run, negative because it's going down, H over R. Okay, and now we've got the equation for that line. Okay, does that make sense? Yeah, yeah, I don't want the length of that thing. If I wanted the length, then I'd have to do like a Pythagorean theorem business, right? But I don't need that here. Um, okay, so right, so that's the equation that describes the hypotenuse of my curve. All right, so if I want to think about the volume of that cone when I spin this triangle around, what I'm really doing is I'm saying, okay, take an arbitrary slice of this thing, Okay, and let's think of that as a really, really thin cylinder. Okay, so how do I find the volume of a cylinder? Well, what's the area of a circle? Pi r squared. And so the volume of a cylinder would be pi r squared times the height, whatever the thickness is. Okay, now if my thickness is really teeny, okay, so my volume would be some sort of integral. Okay, what's the area of, let me erase a little bit here. What would be the area, or sorry, the volume of the, so take that red slice that I made. If I spin it around, it describes a real thin cylinder, right? What's the radius of it? And what's the height of it? Those are the two things we need to know, right? Well, I need to know what the radius is, and I need to know what the thickness is. Okay? What's the thickness of the red line? Yeah, what should I call it? Well, good question, right? Well, this being a calculus class, what's a good idea? How about d something?
Uh, sure.
Okay, why d something, right? Well, I'm thinking about that as being sort of an infinitely thin slice. And what's an infinitely small quantity? A d whatever. Okay, x, y, in this case, h, just because that's the variable that I chose here. Right? I didn't have to pick h, but I did. Okay, is that okay? All right, so that's the thickness of the thing, but what's the radius of it? Well, I need to know what the distance is across this red line. So I need to know what this point is and that point is. Okay, so what is the coordinates of, here, let me put it in a different color so it's easier to see. What are the coordinates of the two blue points?
Are we saying that's halfway? Is that anything? Like, is there any?
No, I drew it sort of roughly halfway, but think of it as being anywhere along that triangle. Okay, so what we should write down should be in terms of variables, not specific numbers.
Right.
Okay, well, because we don't know exactly where that line is. So let's take the left-hand blue point, this guy here. What are its coordinates? That one should be easy. What's its first coordinate? Definitely a 0, right? Because it's where I put the origin. What would be its second coordinate? We do not know, but what's a variable to represent that? Yeah, little h. Okay, so it's someplace on the h-axis, right? So let's call that h. Where is it? I don't know. Okay, but that's okay because I'm letting h be a variable, so it could be anywhere along there. Sure. Yeah. Well, okay. So I'm thinking of what is the specific height of this object, capital H. What is the variable that represents where you are along the vertical axis? Little h. Okay. Um, yeah. Is that okay? I mean, I probably shouldn't have done this. I probably should have used X and Y here, but they'll hire just anybody to teach math around here, right? I mean, this is Crawfordsville, right?
So then for the equation,
Hmm.
that's also h.
Little h, yeah. Well, this one here, we have both of them, right? So the variable is little h. Think of that like y, and the other variable, the horizontal variable is r. Think of it like x, and then the specific numbers are the two capitals. Okay, which this is sort of a deep philosophical thing. I'm thinking of capital H and capital R as unknown quantities, and little h and little r as variables. What's the difference between the two? Turn 21, bring a nice bottle of wine over. We'll sit out on my back porch and talk. Okay. Yeah, go ahead. Sorry.
is half quantity, so it's constant. They have
Mhm.
the living letters, the variables, so they can change.
Right. Right. It's just that I'm not saying that capital H is 12. I don't know. It's whatever it is. Okay. Yeah, that's sort of the distinction. But it's more fun if I ham it up and say, come drink wine and let's talk, right? All right. Anyway. Um, okay. So we need to figure out what the coordinates are for the second point. Well, I could just say it's that, right? Okay. That's certainly true. Okay. But what I want to do then is, so what's the horizontal distance between those 2 points? It's given by little r, right? Okay, however, if I've already said that I'm going to use dh to represent the thickness here, then when I set up an integral, right, the variable that I use to describe for the function, the thing I'm integrating, should be in terms of little h, not little r, right? So it's kind of like if somebody gave you the integral of y dx, you'd say, wait a minute, y is not in terms of x. I want it in terms of x. And then maybe you'd sit down and do some algebra or something and figure out a formula for y in terms of x. But they should match, right? Well, right now I have something in terms of r, but I want something in terms of h. However, I have a relationship between r and h because I have this equation that we cooked up earlier. How do I solve that for little r? Well, first off, what would I do? Oops. I'd move the capital H over, and then I'd just multiply by the reciprocal of that fraction. So I'd get, hmm? No, because if I flip over the fraction, the h's would cancel, right? Yeah. Okay, is that good? So just algebra. Okay, so now I have this in terms of h, so I can substitute it in up there. Okay, so let me write down the integral that we're going to solve. Okay, now the last thing that I need to do, oh, squared, sorry. So notice what we've done, right? The volume of a little chunk is pi radius squared thickness. The thickness is just really teensy, right? Okay, and then I should get a number out of all of this, right? Am I going to get a number out of this integral as I've written it so far? Why not? Okay, but there's no limits, right? I don't have a number there and there, right? So this is an indefinite integral. What should it be? Should be a definite integral, and in this case, it should go from 0 to capital H. And that 0 looks awful lot like a 6, so let's fix it. Okay, so this integral is the thing that I want to compute. Okay? All right, so let's pause. Questions about the setup of it. We'll figure out how to integrate it in a minute. Okay? Yeah, go ahead.
So that red line you had,
Mm-hmm. Yeah, so the red line, no, it's sort of like, so I'm thinking of, right. that if I take that red line as being sort of an arbitrary representative of a slice, it has a radius, it has a thickness. Okay. If I make the thicknesses really tiny, that's like using a DH. And then the radius is, well, whatever it is, right? And we just figured out a formula for it. So for a specific value of little h, this expression, the pi something squared dh, tells you the volume of that little chunk. Okay. This actually works a lot better if I like have an object and a knife, right? Because imagine, ow, that hurt. Okay, imagine taking a cone and slicing it. Like imagine you had a, okay, I can't imagine that somebody would actually make this, but like, so say you took a block of cheese and somebody off in private carved it into the shape of a cone and then handed it to you. Okay, you want to compute the volume of that cone. Well, you could do so by cutting the cone into lots of really thin circles, figuring out the volume of each circle, and then adding them up, right? Well, that's effectively what we just did. The cutting is like drawing these little red lines that have really thin thicknesses, DH.
So how does that represent the thickness?
Well, in the same way that DX represented the width of the like real teeny tiny rectangles. Like, so let's go back to how did we define the integral, right? Back in even Calc 1. How did you define an integral in Calc 1? We said, okay, I'm going to take this curve, I'm going to draw a bunch of little rectangles, and they're all going to have a small but non-zero width, and then I'm going to call the width of them delta x. So I've got the sum of height of function times width of thing, right? So the sum of f of x delta x, where you're adding up however many rectangles you want. Well, then you said, okay, I'm going to let the number of rectangles go to infinity. And if you did, what did the width go to? Well, your delta x's go to like infinitesimal quantities. And what did we call that? Dx, right? So it's the same thing here. It's just it's a thickness because I'm running vertically instead of horizontally. Okay, yeah.
This is discussion is appropriate question for this class. So we sometimes ignore small differences in points. For example, anticipated ideal calculus is that we can just ignore the extreme small difference. But we sometimes use this use this infinite small difference as a real value. So what is the difference between these values?
No, I understand your confusion. Okay, so what I should say here is that um, no, you're absolutely right. So the question is basically we talk about infinitesimal things, but then we don't. What's going on, right? And mathematicians have been wrestling with this question for 300 years. Okay, to the point where let's see, what was it? Somebody called I forget who infinitesimals the ghosts of departed quantities, whatever the hell that means, right? So yeah, no, you're absolutely right. Okay, so let's maybe try and be a little bit more precise as to what I mean here. If I wanted to approximate the volume of this cone, then I would cut it into some finite number of pieces that each have a finite but small thickness. Okay, so if I cut that thing into 1,000 small slices, right, then each slice would each slice be a cylinder, a really thin one? Not quite, actually. It'd be close, and the reason is they would still all have slopey edges, right? But if it's really small, then a slopey edge and a straight edge are kind of close enough, right? Okay, but again, we're trying to approximate. So you slice it up into 1,000 pieces and approximate it as, let me go over to a new sheet and kind of draw what I mean here. So what about if instead of that, you thought of it as, like so. Okay. So if I found the volume of these red regions, okay, it looked like a circular pyramid, right? So a bunch of like coins stacked up on each other. So you have a quarter, and then on top of that you have a nickel, and then on top of that you have a penny, and then on top of that you have a dime. Okay, because that's the order of the radii, annoyingly. I think so, yeah. Or at least in American currency. Um, oh, don't get me started about coins in other parts of the world. In Japan, the 5 and the 50 yen coin both have holes in them. Okay, in the middle, a square hole. But I don't remember if it's the 5 or the 50. One of them doesn't actually have on it, in at least Latin, or sorry, Hindu Arabic numerals, the value. So you just have to know that that's the 50. In Canada, they don't have a penny. I agree. 100 years ago, pennies were important, but now not so much. Um, and Canada, they also have a coin, $1 coins, and even $2 coins are very common. Um, so I don't think there's a $1 bill or $2 bill in Canada. The smallest bill is a 5. So now here's the fun part. What do they call a $1 coin? A loonie or loon, yeah, because it's got a picture of a loon on it. Now here's the best part. What do they call the $2 coin? A double loonie. No, good. No, they call it a toonie. Looney Toonie, right? Now they also eat poutine, so there's something wrong with them. But anyway, okay. So point being, we've digressed here, right? Just imagine stacking coins on top of each other, right? Well, that's kind of what I've done here. It's just that I've exaggerated the thickness of them. So if I added up the volume of all those little tiny cylinders, I would get an approximation for the volume of the cone. It wouldn't be a very good approximation, but it'd be an approximation, right? Well, what about if I, instead of having what, 7 or so slices, what about if I had 7,000? I'm going to get a much better approximation. Yeah? Okay, so we're in calculus, so what are we in the business of doing next? Well, the sum becomes an integral, and how do we transform from a sum of finite things to an integral of effectively infinitely many? A limit, right? That's the fundamental tool of calculus is the limit. Yeah, Cole. Yeah, like curvy thing. Yeah, okay. No, no, fair question. So if we go back to our little crappy violin shape, right? You're right. The slope, if you will, of the slice's edge would be different each time. Okay, but that's the whole point of the calculus approach to this is if I say, okay, I'm going to take a really thin piece of this, okay, that, well, here, let me not draw it like that. That curve that's at the edge, okay, the thinner I make the slice, what does that curve along the edge look like if I zoom in? More and more like a straight line, okay? And so if I say, all right, I'm going to make the thickness of this thing delta y or something, okay? But then I take the limit as delta y goes to 0, that would be equivalent to saying that the number of slices goes to infinity. Okay, that's again how we went from a sum to an integral, right? Because what was an integral or is an integral, right? What does this mean? It oops, means that, right? Well, okay, so let's back up even further. Let's go back to Calc 1, like the third week in Calc 1. What is the derivative? Slope of the tangent line, okay? That's the sort of geometric meaning, but what fundamentally is the definition of the derivative? Right? So you had a quantity, this thing here, which is the slope of a secant line, right? And a secant line and a tangent line are not the same thing, but they're close if the 2 points that you choose are pretty close together, right? And so that fraction, the difference quotient, approximated the slope of the tangent line. And how did we make it perfect? We threw a limit out front, right? So same thing with the integral, right? We could approximate it by dividing it up into a crap ton of rectangles and adding all those dudes up, right? Well, how do we make it perfect? We take a limit, right? Okay, so salient point here, right, is we're going to use this idea of how the integral was defined and constructed to solve this sort of applied problem of finding the volume of things. Okay, so let's go back down to here, right? So we've got this integral that we've set up, which I claim when we work this out and crunch all the numbers, we're going to get 1/3 pi r squared h, if I've not screwed anything up. Okay. I hope we will because I'll be really embarrassed otherwise. Okay, but I should get that. And why do I know I should get that? Because what are we trying to find the volume of here? Just a cone, right? And that formula you maybe memorized in grade school or didn't. Huh? Okay. All right. So are we content with the setup of this integral and that it really genuinely does describe the volume of the entire cone? The setup of it. Now, working out the integral, that's sort of a separate problem. We'll do that in a minute. Huh? Where is the 1/3? Well, it's going to come because we've got h squared. And what happens when you integrate h squared? What are you going to get? 1/3 h cubed. Ah, huh. It's almost like math works. Yes? Um, yes, Coy, you could do that if you wanted. I wouldn't, but you could. Um, so Coy was noting that we could use some trig here, and I deliberately want to avoid the trig in this case. But yeah, okay. So, all right, so this is the integral that we need to deal with. Copy. All right, so I'm going to go over to new sheet, and do you guys mind if well, actually, no, I'll just draw it underneath here. We won't need that much room. Okay, so that's the integral that we needed to worry about. Okay, so the first thing I need to do is I'm going to put the pi out front just because it's a constant, but then I need to also FOIL out I need to FOIL out the thing because it's something squared, right? Okay, and hopefully I did that correctly. Oh, there should be an H on the middle one. Should have an H right there. There we go. Okay, am I missing anything? Okay, it's R squared, but just capital H, right? Okay, so I've correctly multiplied all this out, hopefully. We? No? Okay, good. All right, so now that I've done that, I can integrate. And so I'm going to get pi negative r squared h cubed over 3h squared minus r squared over h squared, um, plus r squared h. Okay, any disagreements there?
So that first one is supposed to be negative or positive?
Uh,
First term.
oh, it should be positive. Yeah, thank you. So this should be positive and that should be positive because I squared something, right? Okay. The other one should be negative though. Right. Okay. Okay, good. So now what do I have to do? I have to plug in capital H for little h, and I also need to plug in 0 for little h. Now, conveniently, what happens when I plug in 0 for little h? Everything disappears, right? Because I'd have something times 0, something times 0, something times 0. So I don't have to worry about subtracting 0. If I plug in capital H, then I'm going to get r squared times h cubed over 3h squared minus r squared h squared over h plus r squared h. Oui ou non? Okay, so all I did was substitute capital H in for lowercase h. Très bien ou pas bien? Okay, now what can I do? There's a lot of simplification that can happen here because I can cancel a number of these h's, okay? And so what am I going to get here? I'll have pi times 1/3 r squared h minus r squared h plus r squared h. And what happens to the latter two terms? They cancel out. And so what do I get? 1/3 pi r squared h. Wow, I did it.
Like right by.
Huh?
Like right by.
Exactly. You never forget it. Well, it wasn't when you first started, right?
Oh, like you just.
Yeah, like think of you guys and calculus like you're a 7-year old and I just gave you your first mountain bike and said, "Okay, here's a real bumpy trail," right? Whereas previously you'd been on your bike on like a sidewalk in your neighborhood, right? That was nice and smooth and stuff. And before that, you were on the bike that had the training wheels. Okay, so the training wheels came off when you went into Calc 1. The smooth the smooth sidewalk went away when you left Calc 1 and went into Calc 2. Now we're on the bumpy. Exactly. No, that's multivariable calculus thing. So, but point being, right? There's so much more fun out there than just smooth sidewalks. Let's start to explore the hills. Okay, the hills of mathematics. Okay, so yes, Donovan.
So then the original volume equation you put with the integral where it was pi times something squared times dh,
Mm-hmm.
that was the volume of a cylinder. Is that what it was?
Uh, the something, yeah, the without the integral symbol, that's the volume of a single cylinder,
So since
right?
you're taking like a bunch of infinite, that's why you put the integral.
Exactly, because I'm thinking of this as a infinitely many really thin cylinders all right. Okay, and to get back to your point, Kim, that was um, uh, we say th- add up an infinite number of small cylinders, but what we really mean is take the limit of a finite sum, right? It's just that in casual speech, it's easier to just treat an infinite thing. Yeah. Yeah. Well, okay. So the turn 21 and then bring a bottle of wine over to my house, or we could drive up to Canada where the drinking age is 18, and then we're set, right? We can we can go up to Quebec and get some excellent fromage, and I bet you if I pay somebody enough, they'll even make me a cone of fromage that we could sit there and slice up. Um, yes, exactly. Okay, so this uh, this is not exactly how I thought today would go. That's all right, right? Because we've really talked is we haven't done a whole lot of examples, and I was hoping to do more examples. Okay, um, but what we have done is kind of talk through the sort of I don't want to say philosophical, but maybe better put, sort of the first principles of like really what are we doing here? What is the business of integral calculus? Slice it into tiny things and add up all those things. Okay. So in the same way that like last time, what were we trying to do? So if I go back to my cone picture here, last time or Friday, what were we trying to do? We would be trying to find the area of that triangle, right? And we'd say, okay, if I wanted to find the area of this triangle, how would I do it? Well, I would think of this red blob as defining a real thin rectangle that has a width and it has a teeny tiny height. And I would add all those up with an integral. Okay. If I wanted to find the area of the triangle, couldn't I have also sliced it vertically and had my slices running horizontally? Sure. Right. Would it really have made a difference either way here? I mean, the setup would have looked different, but could I have done it either way? Well, for area. Okay. Yeah. Okay. I could have. Right. So then what we've done is we've kicked this up a dimension and said, okay, imagine that you spin this object around, and now my slice is representing a cylinder rather than just like a straight line or area. Okay. Now to the question I just asked a minute ago, could I have sliced this thing vertically for the purpose of finding the volume? Yes, the formulas would be a little different, and it's a little harder to imagine, but I could do it, and that's what we're going to do on Friday: is slice it the other way. Okay. So the method that we've used here, and I really should do one more example at the beginning next time. Um, the method that we've used here is called the method of washers or discs. Okay. Which is I've sliced this thing up almost as if I'm stacking coins on top of each other. Okay. Coins of varying radii. Okay. But I could do this using a method called shells. That's what we'll do on Friday. Now, I say washer, so what's the difference between a coin and a washer? Right. Okay. So a washer, I'm not sure if you two would know this word. Um, so if I have a circle with a hole in the middle, that is called a washer. And you use these things like with bolts and nuts and stuff, right? So if we went to Home Depot, there'd be just bins full of these things, right? So you use it basically to, if you wanted to bolt something down, you'd put a washer, then the bolt, and then on the other end you'd have another washer and the nut, right? And the washer, by being wider, distributes the pressure when you tighten something down, right? So it's better for whatever you're doing. Okay, so that's all I mean is a circle with a hole in the middle. Okay, well, I didn't have any circles with holes in the middle here, but what about if I took, instead of my triangle, what about if I took, well, here, let me draw it a little bigger so it's easier to see. What about if I took this scalene triangle and I spun it around that red axis. Okay, then when I draw a slice, it's like a washer because it's a circular piece, but there's a hole in the middle. And I would have to think about how big that hole is. Okay, all right, so let's do this. Friday, first thing, we'll start with a washer example. Okay, what I'd like you guys to do between now and Friday is look over this is, I think, 7.2 in the book. Read through one of their examples on the washer part and also the disk stuff. Okay, and we'll start with sort of quick questions over that, and then we'll go on to the shells method. Okay. Um, okay. Time flies when you're having fun, doesn't it? Okay. Is that kind of all right? Right. So I know, like, we totally did not get through hardly any examples here, which is unfortunate, but um, yeah. Okay. All right. Okay. See you guys on Friday.